Thank you, George. Hello, good morning, everyone. So, why is this project, why we find this project interesting and important for its activity? If we look to the European airspace, technical delays are responsible for around 5.8% of all delays, which has an economic cost to Europe of something like 2.8 billion euros every year. Please also take into account that technical delays are the second cause of delays, being the first cause reactionary delays. If we take into account that reactionary delays is the late arrival of the aircraft, passengers or crew, we can easily infer that a significant part of the reactionary delays started with a technical delay. So the actual indirect cost will make these numbers grow significantly. Next slide. So, in order to reduce the technical delays, we have to do better line maintenance. And we can go both two ways, either by improving the line maintenance efficiency or also by preventing the faults before they materialize. Regarding the latter, this is the scope of predictive maintenance and similar works, and we are not going to address this on this project. We are going to focus on how we can improve the efficiency of line maintenance activities. Next. What's the issue? In the typical short or medium haul flights in Europe, the turnaround time, so the mean time between the arrival and the departure of the aircraft, is around 45 minutes. If we take into account all activities that occur at turnaround, like deplaning, boarding, cargo, fuel uplift, etc., this leaves maintenance something like 15-20 minutes before they cause an operational interruption. So we easily infer that stress starts to build up rather quickly. Next one. What's the context of the person, of the technician that it's doing its line maintenance works? He usually works alone or in a small team, like 1, 2, 3 guys. He does not have access to all the documents and data that he could probably need. The back office is not aware of in real time of the aircraft status, so they cannot do proper support of the worker. A lot of processes are still paper-based. The format of the manuals is still rather obsolete, and I'll kindly ask you to hold on to this point later. And also, the worker, when he's fixing the aircraft, he's not fully aware of the impact that his decisions have on the airline network as a whole. Next one. On the top of this, in the post-COVID world, aircraft maintenance is facing the same challenges as other industries, which is the high staff turnaround. So a lot of people leaving and coming. This results in losing the accumulated experience. And also the new worker, as this happens frequently, needs to learn fast his job. So this calls for new ways of learning how to do the work and of training. Next one. Remember when I asked you to hold on to that point of the maintenance manuals. So we can see in these two pictures, which are two aircraft from the same company, like 50 or 60 years apart, and they evolved dramatically. But this didn't happen with maintenance manuals. If we go to the first aircraft, how were the maintenance manuals? Well, text on a white sheet of paper with 2D figures. If we go to the second aircraft, the maintenance manual is a white screen with text and 2D figures. So basically, the same format over 50 or 60 years. We just scroll through a screen instead of fiddling through paper sheets. So if the aircraft evolves, it's time for the maintenance manuals also to evolve significantly. Next slide. This is why also in previous projects, we explored new visualization learning techniques of like virtual reality and augmented reality. We learned a lot of its benefits. We also experienced a lot of its shortcomings. And we felt that with extended reality, also with new innovative AI tools, we can try to tame some of the shortcomings that we experience with using virtual or augmented reality. And now I will hand over to Jorge.
Luis, thank you very much. Now, the main goal is to describe the use cases in the project. The main goal of the pilot is to develop different training scenarios, taking advantage of the technology developments to improve efficiency, accuracy, and safety of that training. So both use cases are described here in the table. The first one is named virtual training, which aims to integrate AI tools in an XR environment for the process of training the maintenance process of the wing anti-ice valve. And the second one is to develop a human digital twin to guide junior technicians in performing the maintenance tasks with the same device, with the wing anti-ice valve. So for this pilot, we have the pilot leader, which is TEP, here represented by Luis Oliveira. The technical responsible is Immersive Lives, and we have technical partners, each of one responsible for one or two main technical components, as these ones that are described here, that I will describe in the next slide, but here it shows that the partners involved in this pilot. So the technical components that are part of this pilot are these ones. The workers' data collection and analytics, which is a component that aims to collect human data about the earth rate to detect the stress levels. Workers' digital twins, that will be the shadowing or the shadow operator that will be described in more detail in this webinar. The personalized training content, which will allow to customize the experience, the training to the user experience level. The adaptation component, which aims to provide real-time adaptation of the XR contents. We will have also a component related with image recognition, the XR-enabled AL and NSI models. The generative AI models will be used to create a AI assistant that we will show afterwards. We will have also a training platform that will be the core component of this pilot, that will have also the features that is being described here. So I will now describe these components and depict each of the use cases. Before that, I have here just one slide for the general architecture of this pilot. So the apps will be exploited via XR hardware like the MetaQuest 3. Here in this architecture, we can see the core component, which is the XR5 training platform that will provide the training contents to the user. And we can see also the other components, the ones related with AI, and the other related with the adaptation and the human digital twin, which are those here at the bottom. Here the numbers indicate the use cases 1 and use case 2 by 4.2 and 4.1 for the first use case that I will describe now in more detail. So this is the first use case, and also with the expected results in terms of KPIs. We developed these use cases starting by co-creation activities and workshops between the partners in the project and with the pilots. And these are the main user stories that will be tackled by this use case. as this one, as to know the safety measures, to know how to access the wave device, to know which are the tools to disassemble the wave device, and to know in what order should the technician disassemble. Have here yet the tools, but the tools will be shown in use case 2, in the next use case. But we show in the image depicting each of the user stories for the safety measures. So in this use case, it is an XR-based scenario. It will be mixed reality. So the user here, the technician, the AMT, aircraft maintenance technician, will be in the real environment. So it's on the job operation, and she will have the panels displaying the information here for the safety measures, here for tackling this user story on how to access the wave device that is in the aircraft wing, and in what order should the wave device be disassembled, using the 3D model with exploded views and with 3D workflows. The user can achieve this information. These are the KPIs that are expected, so these are still in progress. We didn't test it. We tested, but not yet we didn't analyze yet these results. So this is the expected values to reduce the task completion time by 10% and to reduce the stress levels also by 10%. Now moving to the second use case. The second use case will be the human digital twin. The main goal will be to tackle these user stories on how to access, which are the tools, and also in what order. The main difference is that in this use case it will be a virtual training in VR. It will not be on the job training. It will be off the job settings in order to the user to gain experience and knowledge about these skills. The first one is on how to access, which are the tools. Here we have the tools already, and in what order should the technician disassemble. Here we will use the human digital twin that will be described in the last part of this webinar. To show what is the approach that will use this human digital twin. Very briefly, the user will have access to information visually on how to conduct the procedure, and when this procedure is conducted by a senior technician. So we can record the behavior of the senior technician and then to show this information visually to a junior technician, for instance, when he is learning the procedure. Now I will move to the demo. It will be a brief demo. I will go over some parts of the video just to show the most important parts that describe these components and features that I was presenting. So this is the video with the AMT and the setting. So it will use the MetaQuest 3 devices. And I will go to the last. So this shows the panels with information superimposed in the real environment. We have some features like the AI assistant, the voice assistant that will address the queries from the AMT that can ask questions and have this response, for instance, for the tools that are needed, and the information is provided from this knowledge base and describe the response. Here we have some kind of related materials that can be videos and images that are shown in the environment. I will now show the 3D models, so we can also upload 3D models here in this use case for the wave device, and the user can see the 3D model and manipulate the model, conducting also exploded views to this model. And we are also developing with UPRC, one of the partners, a way to recognize images for image recognition. And here we show how to the first stage of this process, which is to take the image and to train the AI model. So we are collecting images for training this AI model in recognizing this device, the wave device. And here we show this process. We also collect the data from the worker to inform about stress levels with the watch. And here we have the second use case, which is the virtual one with the tools to conduct the procedure. And the main goal will be to develop this human digital twin, so a senior technician conducting the procedure where the junior learner can see what is being done. So we can record from a senior technician, for instance, on how to conduct the procedure, to disconnect the different plugs, and then afterwards we can see what is the correct procedure, and the junior technician can see what is the correct procedure by this recording that is shown afterwards. And yes, this is mostly the information that I wanted to show. Thank you very much for your attention. I will now hand over to Sarah and David for continuing on this topic. Thank you.
Thank you. Good morning, everyone. Next slide, please. So the main question is in our section, why the adaptive user interface are so useful? So take a look on this slide. From one side, we have a senior operator with maybe 20 years of experience. And on the other side, we have a beginner, perhaps a new hire. When we are in the manufacturing world, these two distinct persons often stand from the exact same machine, and it means that they are using the same software interface. And what is the problem? The problem is that these two different persons have different skills, different knowledge, so also different needs and requirements. That could be the case, for example, that the expert operator is slowed down by too much clutter, while the novice one could be just overwhelmed by the software interface. So, next slide, please. To solve this, we have developed a system using the philosophy called the sentient design. What is the sentient design? Let's imagine like an interface that have a brain. It means that thanks to the artificial intelligence, our system is able to understand who you are and what are your needs in that moment. Next, please. It means that with the sentient AI, that in our system, we are using the AI agents that are able to generate new content and visualization adaptation logic based mainly 2 points. The first one, the implicit personalization data. It means that the model is able to monitor the user behavior and the real-time performance. But the second aspect is the explicit personalization input. Here, the user is able to define their preference and skills or requirements through the natural language prompts. It means that the user doesn't need to learn the software anymore because the software becomes the partner that understands him. Next, please. Then, to test our adaptive logic, we started with the Lego Pilot. We used a Lego forklift as just a model to prove that our system currently works and is able to understand the user profiles and needs. But it is just the beginning because our goal, our next step for the future is to integrate our system, our model for the virtual training system for the TAP pipelines, specifically for the maintenance of the aircraft works. Next, please. Now, let's look at this video and show a few steps of our Lego Pilot. Here you can see the setup. In the setup, the user has the possibility to personalize his experience, and in this case, he chooses the Italian instruction and specified to have a progressive experience. When the training starts, the AI provide below the explanation of why it chooses all elements and content for each interface. For example, if the user often clicks on the image or is very fast, the system understands that the user prefers a visual instruction, and for this, the interface stays minimal. And it is just an example of the explanation that the artificial intelligence can provide to the user.
Next slide, please. So as you saw from the video, the interface was composed of 5 different elements, which were text, images or videos, and the system behind it needs to understand if something needs to be made visible or not to the user. So we have some triggers, which could be explicit triggers, so something that the user explicitly say to the system itself. This is on the initial page where the user describes its skill, the role, how he wants to learn the exercise, the language, or the color of the interface. While we also have some implicit triggers, so the system needs to understand the preference of the user. So based on the interaction history of the user itself, but also of previous users that were similar to the one that is using now the interface in terms of skills, role, competence, and whatever, we need to understand and adapt the interface to not overload the user itself with many information, but only to provide the one that he needs in that specific moment. So next slide, please. So here is a comparison between our model on the right with a statistical logic on the left. A statistical logic means that we take a training sample of many users and we see how they interact with the interface. In this way, we can understand which is the most preferred path or the most interested elements that they want to see. But this means that it will be not customized to the specific user. It will be a one-size-fits-most experience for all the users that is going to interact with the system. Otherwise, with the generative AI model, we can have an hyper-personalized experience because the system continuously learns on the user's preferences and is able to anticipate what the operator can want to see and want to learn. So next slide, please. And so here is the validation case we had with the Lego forklift, and this was in a controlled environment because we already have all the steps to assembly this little Lego piece. But the next solution will be a scalable solution. We need to pass from the Lego case to the aircraft maintenance case or any other operational scenario where we don't have any predefined steps because the system can also learn. We can load any PDF or Word document and the system itself can understand the training scenario and provide all the different steps that are necessary to the user based on their skills and competencies, resulting in a zero setup training. Next. And now I give the floor to Samuele.
Hello everyone, it's Samuele De Loca from Subsea, and in this last section of the webinar, I'm going to present you our worker shadowing and monitoring module in the context of the aircraft maintenance training. Next slide, please. So, as mentioned by George, the objective of the use case 2 of this pilot is to develop a human digital twin able to guide junior technician in performing the maintenance process. To do that, we leverage Cloudite. Cloudite is our industrial Internet of Things based platform that we use in order to create customized data representation of both workers and production system elements. Next slide, please. Here you have an overview of the coded instance specific to the XR5.0 project. You can see in the middle that we have the core components, and the base architecture has been significantly extended in order to integrate many different gateways in order to support the data collection from pilots, and together with different functional modules. With included functional modules are what enables to compute and specify additional insights based on the data that has been modeled within the human digital twin. These modules are further plugged in additional XR components such as the training platform and other components developed by the partners. Next slide, please. In this presentation, we will, you skipped one, but no worries. In this presentation, we will focus on the part about worker shadowing and monitoring. And the goal of this module is to store and provide the shadow of an expert maintenance technician in order to track, monitor, and analyze feedback related to the junior technician instead. So in order to provide both monitoring and feedback support. This module relies on human body part information directly tracked through the MetaQuest headset. So for example, we have the information about head and hands position. We have more than 50 measurements that corresponds to the data which is tracked through the headset, and this data is fed into the cloud platform with a frequency of 10 Hz. So we really have a lot of data. We use this kind of data in order to compute the deviations between the expert sequences and the junior one. But what do I mean by computing the deviation? Next slide, please. In the literature, we have two main approaches of comparison between maintenance sequences. We have trajectory-based comparison that in general focuses on the exact matching of specific body parts coordinates. So basically, we compare the worker motion of the expert with the junior one, performing a point-to-point trajectory matching. Instead, we have a more milestone-based evaluation that aims at representing tasks as milestones. And on these milestones are reached, we are able to move to the next task. And this is used in order to manage the achievement or not of the task. As you can imagine, the first approach focuses more on how the motion is performed by performing motion similarity, basically, while the second approach focuses more on goal achievement. Both have different advantages and limitations. For example, the first one enables you to carefully monitor the motion, but it's not optimized. It's not optimal when there are different ways of performing a motion or different hands through which the motion can be performed. While the second one mainly focuses on whether the task has been achieved or not, but less on how it has been achieved. So next slide. We decided to leverage both approaches by realizing our own hybrid approach that combines motion fidelity with task semantic, basically. In the first version, we developed a trajectory-based approach, but we decided to move to this one in order to shift from a pure trajectory matching toward a more milestone-oriented one. Of course, while still leveraging motion data. Here, the core idea is to detect the key milestone that corresponds to the maintenance procedure phases, while still leveraging trajectory information in order to say and determine how the task was performed and to provide suggestions to the operator. There are different benefits, such as that now we are invariant to both execution speed and operator handedness, and we are also able to provide more contextual feedback thanks to the phase detection. As I said, we still exploit temporal dynamics using body part position in order to say not only if the milestone were reached, but also how. So we are able effectively to provide a functional feedback to the operator. Next slide, please. Here you have an example of how the interface of our module looks like. We have several components, and starting from the top bar, we have a description of which is the procedure that we are monitoring and the specific phase. So for example, in this snapshot, we are in the approach phase. Then on the top left, we have a gauge called overall performance that basically determines an activity score by performing the average body part deviation by matching the expert sequence with the junior one, and provides a result via this color-coded gauge. In general, the lower the deviation, the better the performance, and you can imagine this measure in meters. Actually, there is also the rotational component, so 0.5 would represent 0.5 centimeter if we don't take account the rotation, but that's not really the point. I mean, it still provides a useful representation. Then we have different threshold and module performance related things, but on the top right part, we also have the parts tracking status. This provides an overview of the current performance status. We have 3 different kind of state, which is good, critical, and warning, and these directly correspond to how the different part is performing the movement with respect to the expert sequence. And finally, in the bottom part, we have the suggestion part, which is the most important part for the operator, I would say. As you can see, currently is a textual information, but we are planning to show this information through visual or audio cues directly within the XR device. This provides contextual aware activity feedback based on real-time performance. The one that we currently show is the rule-based approach, so basically an if-else approach based on contextual information, but we are also developing an LLM-based version in order to provide more precise feedback leveraging the information that we have. And finally, I will show you a quick demo of this module. Next slide, please. I kindly ask you to put it full size so that we can see it better, if possible. On the background, you can see the system which was developed by Immersive Labs. And now we are running the demo, so we are in the approach phase. You can see that we are moving to the valve. The performance decreased a lot, as you can see in the bottom left interface, and that's basically because the junior operator took a very different timing to reach the valve with respect to the expert one. But as soon as it starts to locate and reach the valve, you can see that performance is getting better. So now we have a lot of yellow, which means warning. But now moving to the contact phase, performance gets better. You can see that the operator is guided by the shadow. It also has some suggestion that now you cannot really read, but it's there. And it basically says the most important thing that the junior operator should perform in order to effectively perform the operation as the expert one did. There are several phases. So for example, we are performing a turn operation now. And you can see also the performance chart in the middle that describes how the overall sequence was performed. And yeah, now we will move to the next phase. So the operator will slowly detach from the valve and verify that everything is correctly in place. By the way, these are just, let's call them fake phases that we decided in order to test the module, and they do not correspond to the official tap procedure. We will develop this one in later phase. Now the operator is slowly releasing the valve and in the verification phase. And yes, the operation was done, thanks also to the guidance of the shadow and while the monitoring of the operator was in place through our module. That concludes the demo and also my session. So I think we can move to the questionnaire. Thank you all for your attention.
Thank you all for this great and insightful presentation. So now we can move forward to the live survey. I will share with you my screen, and we will go here to Mentimeter tool. So please now grab your phone and scan this QR code. I will wait a bit. Okay. Nice. So I will move to the next slide, in which you will see the first question. So please answer in this question: how useful would a real-time worker shadowing and monitoring system be in your professional context? Choose your answer and then press the button on the bottom, submit. Perfect. Okay. 4 more people should respond. So yes, you choose your answer and then the button submit in the end of the page. Okay, I can move to the next slide. So next question, which capabilities would be most important for you in such a monitoring system? Again, you choose your answer and then the button submit. Nice. Okay. I move to the next slide. Okay, I will stay a little bit more. Perfect. So next slide. Which type of feedback would best support you during a maintenance or training activity? Again, choose your answer and then the button submit in the end. Okay, I will go to the next slide in 3, 2, 1. What should the system primarily monitor to effectively help improve performance? Again, choose your answer and then the button submit. Okay, I will move to the next slide now. Would you or your colleagues be willing to try and use a system providing real-time monitoring and guidance during training or maintenance tasks? Please choose your answer again. Okay, I will move forward now. How relevant were the topics presented to you, to your professional or research interests? Again, you choose your answer. Nice. I will go to the next slide. How interesting did you find the use of XR5.0 technologies for aircraft maintenance training? Great. I will move to the next slide in a couple of seconds. Okay. How interesting did you find the potential of XR5.0 technologies to be generalized to other contexts? Perfect. Nice. Great. So, which part of the webinar did you find most engaging? Here you can write like 1-2 words. Please write your word and then press the button again. Perfect demonstration, video demo, video part, worker shadowing and monitoring system, agree. Yeah, human digital twin. Nice, everything. Great answers. Great. Perfect. So I think I can move forward in a couple of seconds. Demo videos. Nice. Okay. how clear were the presentations overall? Great. So, thank you for your feedback. So now we can have a Q&A section to ask everything that you need any clarification or you need to discuss something about. Feel free.